This video tells us about Hooke's law and sinusoidal motion. You'll need some basic mechanics. You'll need quite a bit of calculus and specifically the inverse sine integral. You'll need to be able to solve differential equations by separating variables and therefore know about general and particular solutions. And at the end there is a bit of work on multiple angle formulae which could be useful. Hooke's law tells us F equals minus k times x. F is the force inside a spring or string, minus means it's a restoring force, x is the extension, and k is a spring rate that will tell us how strong the spring or string is. Because we want motion, not a static situation, we need an acceleration. That's provided by Newton's second law. Having two ways of expressing forces, we can equate them. That tells us that A is minus k over m times x, and we find it useful, as we'll see later, to write out k over m as omega squared. Now, how do we deal with our acceleration? The obvious way is to write A as dv by dt, but if we do that, we find we've got v, t and x, three variables inside the same equation, and that's going to cause us a lot of difficulty. We don't want to go that way. So we could write A as d2x by dt squared. Now we have two variables, x and t, but we also have a second order equation, and that will cause us some more problems. We don't want to go that way. So a third way is to go back to dv by dt. We could use the chain rule to write it as dv by dx times dx by dt. We can recognise dx by dt as v, and therefore my dv by dt becomes v dv by dx. Plugging that into our equation, v dv by dx equals minus omega squared x. I've got a first order equation, and it's only got two variables, v and x. That's the place to start, and that's where we'll go. Now, it's a differential equation, and we can solve it by separating the variables and integrating. My v dv by dx becomes v dv, and we end up with this result. It's a general solution. We have an arbitrary constant. We don't know much about that constant. We don't know anything about it. We just know that we could put a number there. In order to find it, we will need some initial conditions. So consider an oscillation. We only know the speed at the end, at the extreme position, when x is equal to a. V will there be equal to 0. We can plug that in. If v is 0 when x is a, 0 is minus omega squared a squared over 2 plus a k. K is going to be omega squared a squared over 2. We can put that back into our equation for a k, remove the 2's, factorise the omegas, take a square root, and we get a result. Now we could put plus and minus in front of this omega, and that's because as the particle vibrates up and down at the end of the spring, at any particular point it can be moving up or down, plus or minus, with the same speed. Now that hasn't given us sinusoidal motion, although it is a very important equation and one that's often overlooked. To get the sinusoidal motion, we take our equation and we write dx by dt instead of v. We've got another differential equation. We can separate the variables, all the x's on one side, and then we can integrate omega t. I'll put the constant of integration on the one side, and we've got this dx over the square root of a squared minus x squared. Now that's a standard integral, and it's the inverse sine. So omega t plus k is going to be inverse sine of x over a. We're not very keen on inverse sines, and we're not very keen on fractions, so we rearrange the equation first of all to get a sine of omega t plus k, and then to get x equals and avoid the fractions. Now this is good, but k is a problem. It's a general solution. K could be any number. We don't know much about it. We don't know what it does. We don't know what it stands for. So what we need is further initial conditions. Now, the first case is to take our equation and to start timing at the centre of the oscillation. Start timing when x is 0. Yeah? If we do that, we find that 0 is equal to a sine 0 plus k. 0 is equal to a sine k. Now, it could be that a is 0, but we assume that this is moving and therefore there is a non-zero amplitude. Sine k would have to be equal to 0, k is equal to 0, and if we start timing for the centre, the position is given as a sine omega t. We've gone from a general solution to a particular solution, this one depending upon the fact that we're starting our timing from the centre of the swing. Case 2, there's our general solution. We're going to start timing x is a when t is 0. We'll start timing from the end of the swing. So when we do this, a is equal to a sine 0 plus k. Sine k is 1, and k is pi by 2 radians, 90 degrees. That's going to give us this result, omega t plus pi by 2. Now, that's a bit ugly, so we'll do a bit of work on that and see if we can simplify it, and we'll go for sine a plus b as sine a cos b plus cos a sine b. Sine omega t cos of 90 degrees is 0, that term is 0. Sine of pi by 2, sine of 90, that's 1. That simplifies greatly. And if I start timing, I find that x equals a cos omega t. This particular solution, if I start my timing at the end of a swing, and this particular solution, if I start my timing at the beginning of a swing. In general, we can write this equation. I'm using phi instead of k because we now know a lot more about k, about this number and what it does. It's a phase factor. And here, if I'm comparing waves, I can look at how big they are, the amplitude, at how fast they are, the frequency, and at where they start relative to each other, the phase factor. And I've now moved from a very simple example of Hooke's law to show it must have sinusoidal motion at the end.